In this installment, we are going to look at the work elastic potential energy corollary and Hooke's law. So let's define this relationship here. The work elastic potential energy corollary is the work done stretching or compressing an elastic body. So some subject is doing the work. The elastic body, the object, is going to require elastic potential energy equal to that work. So the net work is going to be equal to the change in potential energy of the spring. So let's consider our friend the pangolin again, and that pangolin is tethered to a spring and it tries to walk away. So here we have this, we have a relaxed spring. It is at equilibrium, meaning there are no forces acting on it either way. It's tied to the pangolin, and the pangolin starts to walk away. Now, as this pangolin takes a step, he applies a force, and the spring applies a force backward. And then this pangolin takes another step. The pangolin has to exert a greater force than it did to take the first step. And now the spring exerts a greater force. So at every moment in time, we have the force of the spring pulling back being equal and opposite to the applied force, the force applied by the spring. And so we see this here. Newton's third law: for every action and applied force, there's an equal and opposite reaction, a restoring force, we call it. Okay, so it's equal and opposite to the restoring force. Now, during that time, the spring is elongated, or experiences an elongation, delta x, that is equal to the change in length. And so what we see then is the pangolin is applying a force, but the force is changing, and he's applying a changing force over that displacement. So let's go up here and look at this graph, and let's graph what happened with the pangolin. Well, when there was no elongation, the force applied was 0. So what we have in that situation is that we have, in the beginning, we have an F0 and an X0. F0 equals 0, the initial force is 0, and the initial elongation is 0. And the initial position is 0. So what happens is we apply a force, the pangolin applies a force, and there is a displacement. And what happens is, it turns out, for something that obeys a constant increase in force, that is what Hooke's law is. In an elastic body, whose restoring force increases directly with elongation. And so again, directly means two things: constant slope, and it means a y-intercept of 0. Goes through the origin. Whatever happens to one happens to the other. So this is the relationship we have here. We have this force increasing in a straight line. So this graph, what we can read is, we can read the force, and we can read the elongation. The slope is force over elongation, which has units of newtons per meter. And we can see in this case it's constant. Now, it's pretty easy for us to see that if we had attached a stronger spring to it, for the pangolin to cover the same distance, delta x, he would or she would need to apply a greater force. And so we would see in this case, this is a stronger spring, and this is a weaker spring. And what's different about those two is their slopes. And so that difference in slopes is about the difference in strengths, and that is something we called K, the spring constant. So every particular spring will have its own spring constant, its own strength, that shows up as its slope of the line. So the slope is K, and the area in this case is F times delta X. Let's see, newtons, meters. Wait a minute, well, that's force times distance. The area is the work in this case. And so Hooke's law Elastic body is directly related to elongation. You'll also notice that it follows the equation of a straight line. So we have y equals mx plus b. The y-axis is the force, and in this case it was the applied force. The slope we said is the spring constant. The x-axis is the elongation, and the y-intercept is 0. So Hooke's law is basically F equals kx. So down below we see the force applied is the spring constant times the elongation, or the restoring force, which is equal and opposite to the applied force, is also k delta x with just a negative below it. And again, this is a consequence of Newton's third law. So now let's take a look at this potential energy situation. We have our work, which is equal to the average force times the distance. Now let's note that the force in this case did not remain constant. So we'll take a look at the distance. The pangolin in this case is moving in a straight line in one direction, so that distance we will say is delta x. So our force carries down, our distance is delta x. Now what is that average force? If we were to consider a certain distance, let's say this delta x here, the force increases from 0 up to F. And if we wanted to find the area under that curve, well, we could do the area of a triangle, or we could do the area of a rectangle. Now, the area of the rectangle for underneath this curve, so there's the area of the triangle. The area of the rectangle we would need would be a rectangle half as tall. And so that rectangle that's half as tall would have this area equal to this area, and that means that the height we're looking for is F over 2. So the force we're going to use is not the instantaneous force, it's going to be half the instantaneous force. And that also occurs because the initial force is 0. This height will always be F over 2. So the average force is F over 2. And delta x is delta x. Now, what we said, though, is that the force at any particular time, the instantaneous force, is equal to k delta x. And delta x, since x0 equals 0, delta x is x. So if f is k delta x, and delta x is x, then F applied equals kx. So the F applied becomes kx, and we said delta x is x, and we'll remove the coefficient out front, and we have kx and delta x, and 1/2 kx times delta x, and delta x is x, gives us 1/2 kx squared. So the work done by the applied force is 1/2 kx squared. Now the idea here then, if all that work goes into the potential energy of the spring, then that work is equal to the potential energy of the spring is equal to 1/2 kx squared. And since the change in potential energy, since the total potential energy is equal to 1/2 kx squared, and we started with the potential energy of the spring of 0, then the change in potential energy of the spring is equal to 1/2 k times the change in x squared. In other words, any change in energy, so if we do work from here to here, that first segment of delta x, and then we do work here to here, well, the change in potential energy that we have at this location to this change in location, the second change in location, is due to the change in x's. The change in x here. And so that is the work, elastic potential energy, and Hooke's law. Hooke's law is F equals kx, or a directly proportional relationship between the elongation and the applied force. The restoring force is negative kx. The applied force is always equal and opposite to the restoring force, and that's Hooke's law. Applying Hooke's law to work, if all of the energy is all the work done is converted to potential energy of the spring, then the total potential energy of the spring is equal to 1/2 kx squared. And any change in potential energy is going to be due to 1/2 K times the change in length squared.